Numerical Computation, Chapter 4, Additional Video Number 1. This is an additional video which you can view after you have completed the regular videos for Chapter 4. The topic of Chapter 4 was numerical integration, and we have learned various methods, various integration rules to find approximations to integrals of a function. Here in this video, we take a look at all these algorithms in a more abstract setting. To fix the ideas, let's consider a quadrature rule for integrating a function f over the interval from -1 to 1. So in a sense, all the rules we have seen are in the core based on polynomial interpolations of this function f through the nodes. So let's fix some notation and let's call the nodes to be x0, x1, and xn. So we have n+1 nodes. We first look at the closed Newton-Cotes formulas. This is a numerical integration rule with a specific set of nodes which includes two endpoints. So let's consider a set of uniformly spaced nodes and let h denote the interval length, which would be 2 over n, and then the nodes then can be written as the left end of the interval, which is -1 plus I times h, where I runs from 0, 1 to n. We now write out an interpolation polynomial of a function f, where the interpolation points are chosen to be the nodes. One can use the Lagrange form and write it as the follows. So the polynomial denoted as Pn is the function value at the node times the cardinal function at that point. And you go through all the nodes and you add them up. And this is the Lagrange form. So we are familiar with this interpolation already in Chapter 2. We can now integrate both sides of this from -1 to 1 in x, and then on the left hand side we get the integral, and on the right hand side, because there are finitely many terms, so I could integrate each of them and then add up afterwards. So I have the summation of the integral of f at xi times li x dx, and since the number f at xi is a constant with respect to x, I can pull it out of the integration sign. Therefore, I only have this, and where these li's are the cardinal functions, and they are given once the nodes xi's are given. So this integral can be evaluated once the xi's are given by integrating the cardinal function, and we denote this integral by wi, and we can write our rule with this shorthand notation. And here these wi's are numbers, and they are also called the weights. So the rule becomes multiply the function value at xi by the corresponding weights and then sum them up, and that is your numerical integration rule. Let's take some examples. If n equals 1, then we are taking 2 points, which means the two endpoints. The interpolating polynomial would be a linear polynomial connecting the two endpoints, and we know that gives us the trapezoid rule. increase n by 1, now consider n equals 2, then we have 3 points, the two endpoints of the interval and the midpoint. And the polynomial going through that will be a quadratic polynomial, and we know that the resulting rule will be the Simpson's rule. And with n equals 3, we get the so-called Simpson's 3/8 rule, and which takes this following form. So the function value f at xi appearing here, and they are multiplied by these coefficients. And the coefficient in front of each f is exactly the integrated value of the cardinal function. Okay, so one get 1/4 in front of x0 and 3/4 in front of x1 and x2, and again 1/4 in front of x3. Giving one more example for n equals 4, and one gets 5 points, and the resulting integrating rule is known as the Bowles rule or the Milnor's rule, and the coefficients are given here. They are nothing but the work of integrating the cardinal functions. We do notice that there's some symmetry which could simplify your computation. So the midpoint is here 12, and the coefficients are symmetric on the left and right of it, so both 32 over 45, and you take 1 point apart, and then it's 7 over 45. Now it is also rather easy to check that for each given n, the corresponding rule will be exact for all polynomials of degree n. If one does not include the endpoints as the points to integrate, this leads to a family of rules called open Newton-Cotes formula. So let's consider again uniformly spaced grid, but without including the endpoint. So h now is 2 over m plus 2, and where the xi's will be -1 plus I plus 1h. So when I is 0, I will be at the point -1 plus h, that is not at the boundary. So carrying out in a similar fashion, one can write out the integration rule as taking the function value at the nodes multiplied by the corresponding weight and sum them up. And the weights wi tilde here is computed as the integral of the corresponding cardinal function in this case. So here the li tildes for I from 0 to n, that's a set of cardinal function taking the nodes x0, x1 all the way to xn. And again, one can easily verify the degree of precision here will be at least n. We would like to comment that the open Newton-Cotes formulas are not as commonly used as the closed one. So in general, for any n plus 0.1 arbitrary points, let's denote them by x0, x1 to xn, they doesn't have to be uniformly spaced. But once you have chosen those points, then you can find an interpolating polynomial of your function through those points, and then you can define a numerical integration rule just as we have discussed. So here the rule will take the form as the function evaluated at the node multiplied by the weight, and where the weight is just the integral of the corresponding cardinal functions. So if your nodes are not uniformly distributed, and you just have to define the cardinal functions accordingly. It is clear that any interpolation rule based on n+1 points will have degree of accuracy at least n. This follows from the fact that if you have a polynomial of degree n and you interpolate it through n+1 unique points, you will get the polynomial back. The previous two examples we gave are examples where the points xi are given in advance, and then one tries to find a integration quadrature for it. Now we can change the idea and say that the location of those points are not specified in advance, but then we try to find them in an optimal way such that the accuracy is as high as possible. This idea leads to Gaussian quadrature. Now let's consider a rule for the integral in a more general setting, and I wish to integrate from -1 to 1 wx times fx dx. So here w is a weight function, and I want to approximate this integration by evaluating the function at points x0, x1, and xn, and then multiply them by suitable weights wk and add them up. So far in all our previous discussions, we have used wx is constant 1, so we were simply integrating a function f. But in many applications, one would encounter an integral of this where the w is a positive function. If we set f to be Lix, the cardinal function at xi, then we can evaluate this expression, and then we would have only an wi on the right hand side. Therefore, wi would be the integral of a cardinal function times wx dx. By using those as the weights, we see that the rule is exact for polynomials of degree n. Here the degree is obtained for any choices of the set of points x0, x1, xn. So we call the attention that the rule we are called formula A as our label, and for the weight function we call this formula B. Now our goal now is to design a rule such that the formula A is exact for polynomials of degree much higher, and in fact we want it to be degree 2n+1. This means the rule is exact for fx equal x to the power k, for k from 0, 1, 2 all the way to 2n+1. We want to achieve this by suitably choosing the points xi. Towards this goal, we now define an inner product of two functions, f and g, as follows. This is a notation of the inner product, and the inner product is the integral of f times g times the weight function w. And now we start from the set of kind of a basis function for the polynomials, 1, x squared, all the powers of x, to x to the power 2n+1. Starting from that set, we carry out a Gram-Schmidt orthogonalization procedure, and we generate a family of orthogonal polynomials, and we denote them by p0, p1, p2, and all the way to p2n+1. One knows that such a procedure is possible if the set of functions we use are linearly independent. Let's look at the details of this procedure. So we need a starting point. So we choose our first polynomial P0 at level 0 to be a polynomial of degree 0, which is a constant 1. Once that's chosen, you can use that to form the next polynomial, P1. P1 is formed as taking this function x here and subtract this part, and one can view this part as the projection of x onto the function p0. Okay, so this will be the part, the length of the projection, and that is, the length is multiplied by the function itself. So this whole thing becomes the projection. And if you take a function x and minus its projection with respect to the inner product, what you get as a result is something that's orthogonal to the function that you project with. So here P0 is 1, and these inner products are just integrals. So, and you integrate 1 times 1, you get a 2, so I get a 1/2. And then this integral here is from -1 to 1, P0 times x times w of x. So once you have formed P0 and P1, you can go on and form the function P2, and the goal is to have P2 being perpendicular, orthogonal to both P1 and P0. So the procedure would be starting with the function x squared, which cannot be represented by P0 or P1, and then take away from it the function x2 projected down to P0, which is here, and also the part of function x2 projected down to P1 here. After one removes those two parts, what remains will be a function that's orthogonal to both P0 and P1. Okay, so some details, since we know what P0 is, so that inner product gives me 2, and then I write out the detail of this inner product, which is an integral. And here, okay, I put P1 over here and P1, this one could work out once you work out that. And then this integral here is just that inner product. And you can continue this process, and the general formula for step k, when you want to compute pk with the polynomials p0, p1 all the way to pk minus 1 already computed, is the following. So you start with the function xk, which cannot be represented by all the previous polynomials, and then you take away from it all these projections. So xk projected down to the function pj of x, and j goes from 0 to k minus 1. And what you have in the end, this function here, will be perpendicular to all the pj's, j ranging from 0 to k minus 1. So some observations. We see that by this way of construction, we see all the polynomials are monic, that is, the leading term, the term with the highest power, would always carry coefficient 1. Moreover, all these functions are orthogonal to each other. That is, if you check the inner product between pi and pj, which is this integral, that will be 0 for all I different from j. Therefore, this set of functions P0, P1, and Pn that's generated by this orthogonalization procedure, they form a basis for all polynomials of degree n, and actually they form an orthogonal basis for Pn, orthogonal with respect to the inner product that we just defined. So in particular, the following property might be the most useful one. And then Pn plus 1, if it's generated by the procedure, then it is orthogonal to all polynomials of degree n, which is less than this degree. So Pn plus 1 inner product g is 0 for every g belong to polynomial of degree n. Now the next theorem relates the zeros of these polynomials with Gaussian quadrature. The theorem says, let Pi be a family of orthogonal polynomials with respect to the weight function Wx over the interval -1, 1. And then let x0, x1, xn be the zeros of the polynomial Pn plus 1. Then the quadrature rule A, the one we set up, with the weight function Wi as defined in formula B, would be exact for fx equals xk, for k now ranging from 0, 1, and all the way to 2n plus 1. So this means if we use the zeros of Pn plus 1 to be the nodes, then we will get a quadrature rule that whose degree of precision would be 2n. Now let's look at a proof for this theorem. So since now these x, the nodes we choose, they are zeros of this polynomial Pn plus 1, then clearly we have this relation. Pn plus 1 evaluated at all these xi's will be 0. By construction, we also already know that the rule will be exact for any function that is a polynomial of degree n. What remains to show, what is non-trivial, is actually we could raise the degree of precision much higher. And now we suppose that f is actually a polynomial of degree at most 2n plus 1. And then we can write f as follows. We write f as Pn plus 1, the polynomial of degree n, and multiply by a q of x and plus an r of x. And here both q and r are polynomials of degree at most n. You can think that as follows, that you take this polynomial f and then you do a polynomial division. You divide this polynomial f by this polynomial Pn plus 1. Then this r here will be the remainder and this q will be the quotient. Then we apply the integration rule to f. So the integration rule on f will be the integration rule to this expression, because we rewrite our f like that. And now we use the fact that the xi's are zeros of Pn plus 1. Therefore, Pn plus 1 evaluated at any xi shall be 0. Then this first term is gone. And removing that, and we see we are summing up wi times the remainder r term evaluated at xi. And this is like applying our rule on this polynomial r. and we know R will be a polynomial of degree at most n. And now, on the other hand, let's look at the exact value of this integral from -1 to 1 of w times f. And we plug in the expression for f, that we rewrite it like that. And we apply the distribution rule. We distributed the multiplication into each, and we break it up into two integral terms. So we integrate the first part, which is w times r, and the second part, which is w times q times p and plus 1. And now what is really interesting is that this second integral here, it is exactly the inner product between pm plus 1 and q. Recall the definition we made. And we also know these polynomial p's are constructed such that pm plus 1 is orthogonal to all polynomials of degree less than or equal to n. Therefore, this is 0, the inner product, so this term is 0, and the only non-zero term is the first one, which we write here. So this first term is basically integrating this function r here, the remainder. Now by construction, we know this remainder is a polynomial of degree n. And for any function that's a polynomial of degree n, my rule is exact. That is, applying the rule on it, I'll exactly get the integral. So remember, on the previous page, we showed that this is the same as applying the rule onto f. And then now we show it equals the integral, and then we show that the integral equals the integral of f. And then put them together, and we get applying the rule on f is exactly equal to the integral of f. And this relation holds for every f that is in the set of polynomial of degree 2n plus 1. And that is exactly what we need to prove. Okay, that's all for this video. Hope you enjoyed it. Thanks for watching.